Hola, y'all. How is everyone today? Chapter 3, tree height versus volume. Yeah, that's what we want. It's just you and me, Cheyenne. Oh, and Eve. Oh, and Jaleesa. Nice. All right, let's do this. I want to kick off today by showing you, kind of let's stand back for a minute and look at calculus in the bigger picture. I don't know if you're seeing it completely, like what it can do, and this pertains to what we've been looking at recently. But notice what I want to say is, like, you take this class and you pass it, and awesome, people say good, you can go on with your degree. But you also want to be good at your job. You also want to get a job, and there actually is a reason that you're being asked to take calculus, and I want to kind of show you what that really looks like. And I want to show you also what the big picture of math is really supposed to be about. And so here's an example of, well, something a forester might be interested in, which would be, you probably can guess there'd be some relationship between the height of a tree and a volume of a tree, in the sense that if they get taller, they also get wider. And so tall trees are big trees. And you may also be able to appreciate it's kind of hard to measure the volume of a tree, but it's not super hard to measure the height, although that takes trigonometry all by itself, but that's another story. And so this is what math kind of really looks like. It really could look like, in the sense that somebody could actually gather data. And so over here, you start with data. You have a 12-foot tree, you measure its volume. You have a 20-foot tree, you measure its volume. And so you get a little bit of data on a particular tree. And so algebra is about expressing relationships, and you start with ordered pairs or data. And then when you look at the graph of that data, and I use technology in Excel to do that, I get this graph. And so you say, yeah, look at that, duh. As height gets bigger, volume gets bigger. But notice these aren't scattered everywhere. Like, there's definitely a relationship there. And to me, at a glance right now, it kind of looks like it's, well, linear. It looks like a line. It's kind of growing, well, with the same slope, you might say, now that you know calculus. And so let's look at that a little more deeply. So you first start with an ordered pair, then you look at a graph. And the beauty of this is basically the power of prediction. In other words, you can imagine a forester saying, I'd like to harvest the tree for lumber for houses when it gets to, say, 1,500 cubic feet of volume. That's its volume, and then we'll be ready to harvest. And so, when is that going to happen? Or, how tall is the tree when that happens, so that I can kind of know, and so forth. So now I have a graph, and ultimately, in Excel anyway, there's this thing called regression. And I hope you've been taught this by some math teacher before me. Otherwise, we collectively as mathematicians have not done our job. But regression is the process where I need to edit that. Regression is the process where you turn ordered pairs into some kind of an equation. And notice a line is not bad here at all. It's like pretty decent. However, maybe now you can see that you couldn't see before, that it actually does have a little bit of an upward curvature to it. And so maybe a line isn't the best choice. And you studied a whole bunch of algebra, and the idea behind that is you would say, well, there are other graphs that kind of have upward curves to them. And notice, kind of nice in Excel, that you're even getting like a little preview over here. Like an exponential is kind of an upward curve. So you might say, well, I think it's curved, I'll try that one. But maybe that exponential growth is growth that kind of starts off slow and then it really takes off. And so notice, although it's curved nice, it doesn't fit that very well. And so an exponential equation isn't a very good model, apparently. And then here you can see logarithmic curves curve downwards, which again, you at one time knew, but probably don't know deeply. And so this is a dumb thing to try, because that isn't downwardly curved. And so that's terrible. And then polynomials collectively, notice it says order 2 over here. That's like a squared equation, like a parabola. Or I could say, what about a cubed equation? Notice that's a darn good fit. Cubed equation, that's a really good fit. Squared equation's a pretty good fit. Power equations have upward curved equations. Hey, that's a pretty good fit too. For the sake of the fact that we've been studying power equations lately, and also because you haven't really seen these much, probably have never even heard that word applied to a particular type of equation. I'm going to use that one just because it's a little more interesting. Although I think you'd agree that just at a glance, that cubed equation right there just looks like money, man. I think it's right on the money. So a cubed equation would be awesome, even better. But let's look at a power equation. Now, there's a couple things I can do here that are really cool. One of them is I can tell what the equation is, and I can even display that equation on the chart. So I'm going to go over here and make it nice and big. So I guess, would you agree that we really own the relationship now between the height of a tree and the volume of a tree? And there's 3 ways to express that: ordered pairs, which we went and collected data; a graph, all I have to do is plot them; and now an equation. And equations are the coolest because I can now predict the future, well, real algebraically. And so, as I said, and we won't do this, but if the forester said, we're interested in the tree when it gets to 1,500 cubic feet of volume, in other words, y is 1,500, you, as a graduate of algebra, should be able to take this equation right here. And again, I'd be willing to bet money that at least 2/3 of you could not do this right now, which again is kind of our fault, not so much yours, although it's partially yours. But if I went in here, and you might try this just on scratch paper, if I said y was 1,500, like, could you solve for x and like find the height of the tree that would be the case? And I say it's hard because notice that exponent is ugly. It's 1.47. Like, that's not squared, it's not cubed. It's kind of an ugly exponent. And my guess is that might trip you up a little bit. But that's what it means to speak the language of algebra. Now that I have this equation, I should be able to do the easy thing, which is say, hey, I just found a tree that's 100 feet tall. So I throw in x as 100, and then I say, what would the volume of that tree be? The equation is the coolest way to express it because this is teeny pithy little formula that just tells me every tree's height and volume. And so that's really cool, but you got to be able to speak the language. It's an intimidating formula. Cool. And so my question here is kind of like, what does calculus add to this discussion? So now we own the relationship. And again, could you do this? Like you left with a degree from RCC, or maybe you go on to a 4-year degree and you took all this math stuff. Can you actually do anything with it? And again, I put the fault for that on us if the answer for you is no. But this is what's cool about algebra, is the ability to find a relationship between things. And so if let's say you're a doctor, doctors have to do this. And so you're modeling some patient whose cholesterol is dropping because you're giving them medication. Would you be able to take data every time they come and see you every, say, 6 months, and you can record, the time, how the time has changed, and you can record what their cholesterol level is. And now you can find a formula, predict the future, and you can tell them, hey, we need to get you down to 180. And if I plug 180 in for Y and solve for X, that's, 15 months. And so 15 months from now, if you keep up what you're doing, you're going to be off that medication. And, wouldn't that be cool to be able to do that? If you're a patient, wouldn't that be nice if somebody could actually do something with math that's real, like actually helps people? Or maybe more practically for you, if you're getting a job, would you be impressed if somebody just said, hey, let me show you something I can do. I'm going to be a veterinarian, and, calculus is stupid. I don't need calculus to help dogs. And yet, what if you were actually treating a dog and you were monitoring that they were getting better, treating a horse? And, if you applied for that job and you said, hey, here's something I can do because I know math really well, would you give that person that job? Like, is that pretty cool to be able to know how to do? My point is, don't just sit there in your classes and try to pass them. Like, ask deeper questions, like educate yourself, get an education, become somebody who can actually kick ass at your job and, do a really good job, get paid more, actually get a job. And to that end, as I've been saying, it's kind of our fault because we never give you really any realistic questions like this, or we don't do it often enough. Could you do all of the algebra that you're sort of already supposed to know? But now let's move one step further and say, what would calculus say about this? And so I want you to begin thinking about this while while I copy this over to our screens that I can write on and so forth. You know, what would calculus say about this? What would calculus allow you to do about this? I'm going to ask you / teach you. So I'm going to take a picture of this. That should do it. And let's say goodbye to the nice Excel page. Let's share the screen of the iPad. Get ourselves a new note. And so again, we're taking kind of a 3,000 foot look at, you know, like what can calculus do in the bigger scheme of things. And so now I'm going to bring that picture in. And you come. Can't believe how cool technology is. Crop that dude off. Should have shut my window. It's all bright over there on the right hand side. There we go. Lovely. So of course, you know, in calculus, I guess we take derivatives, right? That's what we do in Calc 1. We take derivatives. And so we find things like y prime. And so just so that it's a little simpler, let me round this off and say that's 2.139. So let's just call it 2.14. And then x is raised to the 1.476. So let's call it 1.48. My question is, can you find the derivative of that? And then more importantly, do you know what good that does? So let's find y prime, and let's find y prime of 20, and let's find y prime of 80. Like, you never just take a derivative, you use it to do something. And again, I picked the power equation as a model just because, hey, we just recently learned how to take derivatives of these via a shortcut. We have the power rule, and that's why it's called the power rule, because this is called a power equation. X is raised to a number. That's what makes it a power equation. If it was raised to a letter, it'd be exponential. But you should be able to take the derivative of that right now, even though that's, you know, a little different. You're used to seeing the sterile book questions where it's x to the second or x to the third. It's like whole numbers. It doesn't have to be whole numbers.
So after you find the derivative, is the use of the derivative in this equation if you could pinpoint a point of x and it tells you how fast it's growing at that point?
Yeah, good thought. I'm not going to answer that just yet because I want other people to think about it, but think about what Eve just said. She's like, what does, you know, 20, if you put 20 into the derivative equation mean? She said something about, does that mean how fast the tree is growing or something like that?
It seems a little kind of awkward in this one because in other ones we had stuff like, you know, I guess time or whatever was the assumption for x, but this one's kind of like two things that don't really they're related, but they don't strictly depend on the other. Like the amount of height and volume seem kind of independent in some ways.
Yeah, they're related for sure. And notice we didn't know they were related until we looked at the graph. And by the way, this is real data. This is from our Math 96 class, and I wrote that book, and this data is real data, like it's not fake. So the graph would say, well, oddly, they actually are related. And then to your point, Felix, the units are also weird. So notice our y, and I'm just going to highlight this over here. Our y is ultimately volume, and its units are cubic feet, which is kind of weird. And our height, our x, is feet, and that makes sense. Our height would be a length. So cubic feet of wood. And so that's definitely part of the answer to this. But no, there actually is a relationship, but it's just unusual units. So doesn't the power rule say you take the exponent 1.48, multiply it by that coefficient in front, and you get like 3.17 approximately. And then it's x to the what power?
0.48.
Yeah, 0.48. And notice that's about a half, which means that's actually right around a square root. It's almost like the square root of x. In a sense, a person might say, well, I'll just write it as the square root of x. But that's just kind of interesting to note. And so notice that's kind of cool, if you will, that the derivative is sort of a square root in this case. But of course, now it's not hard. What we have now is a recipe. What we've been doing lately is just a recipe for slope, right? That's what derivatives mean. But again, slope is too sterile. Slope is just for mathematicians. It's like a slope of a curve, but slope has a meaning. Really, in this case, nobody cares about the slope. They really care about it as, well, what a slope really is, which is that's the rate of change. And if there are units involved, as there are here, or the units actually mean things, we have feet and cubic feet, then rate of change is pretty powerful. And as Felix said, rate of change feels much nicer when it's something like, how many feet does the tree grow per year? Like feet per year, that as a rate of change would feel better. But I purposely picked this because it's, oftentimes it's time that's the x-axis unit, but it doesn't have to be. And so this is interesting, I think. And as I said, I think the rate of growth of the tree being feet per year would be an interesting thing too. Like, how fast is the tree growing?
I don't know if it's just me, but you're cutting in and out, kind of. I don't know if it's just me though.
Yeah, I thought
same for me.
I thought it was the same for me too. I thought I was cutting out, but it seems like you're definitely cutting out a lot.
Okay.
Yeah, same over here.
Sorry about that. I don't know what's going on. Let me check my internet connection. Bought a new router, hooked it all up. Everything should be working good since I have full bars. Maybe I need to talk slower too. Hopefully that'll go away. Let's see. To the extent that it doesn't, feel free to ask me to repeat something. I can sometimes tell when this is happening because I see you guys and you're like totally frozen and then you move again. And so I know it froze for a second or two. You're probably seeing me do the same thing. But no, I think it is me because it's happening to all of you. So let's see, if you put 20 in there, of course, that's easy. You say, okay, great, 3.17 times 20 raised to the 0.48 power. And just to keep it simple, I'm going to just say it's 13.35, but I'm just going to say it's 13 so we can speak about it, because I'm interested in the meaning of this more than I am the exact answer. And yet when I plug 80 in, I get 25.96, or about 26. So as a teacher, I could give you this question and say, what's y prime of 20? And you could put 13 on the test, and we're like high-fiving that you just got that right, because you know the power rule, you understand what slope is and so forth. But my point is we've done nothing yet in terms of actually making this useful. Like, what does 13 actually mean? What does this add to the discussion? What does this tell the forester about the tree's growth? That's kind of cool. So think about that. But secondly, here's something that should bother you. We just went to 20. I don't know, what does that slope look like to you? Certainly doesn't look like 13. Would you agree with that?
Well, the scale isn't 1-to-1. It's like 200 to 20.
Yeah, see what the boxes are worth? Like, this is super common because I'm really gathering data, and the numbers are just different. The X's are fairly small numbers and the Y's are fairly big. And so the graph, and I didn't do this, Excel did this automatically. It chose a scale that made the graph work nice. And notice the Y scale, the boxes are worth a lot more. And so that doesn't look like a slope of 13 anymore. The graph has been kind of crushed. And so, again, that's much more realistic than the questions I've been giving you. And then of course, when you get out here to 80, which notice 80 is not even on the screen. I almost would have to like extend it a little bit. But out there, the slope, of course, it's steeper, right? So I'm not surprised the slope is steeper. I'm not surprised, but I am surprised it's 13 and 26. That's really hard to see in this. But now we get to the most important part, like what, and Eve was hinting at this herself, but could you explain to somebody what that 13 means? It's not slope, that's useless. It's rate of change, but rate of change of what?
I think if you go like just to the basic, it's like dy over dx, and then the change in y over x, and then like what does y mean and what does x mean? The volume over the length. What is it? Sorry, height.
So if
feet
x
squared or feet cubed, and then just the change of that, and then
equals height, which is 20 in this case, and then the volume equals 13, which means that at height 20, it's changing at 13 feet volume per second per height. I think I'm
At feet cubed added to the volume.
Love it. Good statements all the way around. My screen is not sharing right now. Just a second. But you're exactly right. What Martin started off with was great. And I missed some of what you guys said because I froze in there. But it's like, isn't slope change of y over change of x? Well, what are the units of y? They're cubic feet. What are the units of x? They're feet. So you're talking about how cubic feet changes relative of volume changes to feet changes of height. That's what you're talking about here. Let's see. Just going to try stopping sharing and starting over again. So that's exactly right. And so the point is this slope is always two numbers. And so 13 is 13 over 1. And if you just add those units to it over there, 13 cubic feet and 1 foot. And then you also notice that you don't necessarily write that down, but if you notice those are positive numbers and you just put that into words, now you actually are talking about something that's useful. What this is saying is for every foot of height the tree grows in height, it gets 13 cubic feet bigger in volume. But that isn't constant. That's what makes calculus so interesting, because when you get out to 80 feet, what's a foot worth out there? What's a growth of 1 foot worth out there? Well, that's actually a growth of 26 cubic feet. So it's like its volume, a foot is worth more when the tree is taller. Do you see what I'm saying? Like this is what calculus is telling us. And so, a forester might say, well, based on this math I did right here, let's consider growth rate and it's kind of wait longer because we're way out there, we're getting a lot bigger answer. And of course you can try to predict the future. This is a little dangerous to go clear out to a 200-foot tree. Maybe this tree really does grow 200 feet tall, but we're talking about 120 years from now. And so can we assume nature is going to provide for the tree in exactly the same way it is? Well, it'd be our best guess. It's not wrong to do that, but it's risky because you're way out there. So if I stick 200 into this, going to do that really fast. To insert a 0, I got 40. So 40 cubic feet per foot, and the units are so weird. That's why I picked it. But it's like 40 cubic feet of growth per every foot of growth in height, and so it's it's growing way faster out there. And so the conclusion would be, hey, let's wait. Let's kind of wait because this thing's growing really fast. One more year out there and we'll be 40 feet bigger, and that's worth a lot of money, or it makes sense. So do you see why growth rate is just kind of a cool thing to add to your knowledge? I mean, it just gives you one more thing to think about with respect to your relationship that you're talking about here, rate of change. Hey, how are things changing? That's the big picture of both algebra and calculus kind of all rolled into one. No one's ever going to walk up to you and say, hey, I got this equation. Can you help me solve it? Like, you have to be the one to get it for yourself. You have to be the one to do regression and choose wisely as to which equation makes the most sense to model it. You got to get that yourself. The only access you have to relationships in the real world is data that you could collect. And then once you have that data, you could graph it. It's not hard to graph something, although it's nice to use technology as I did. And again, my guess is a lot of you, nobody ever taught you regression, which is kind of not cool. But if you want to stay after class and ask me those kinds of questions, that'd be cool. And now you kind of see what calculus adds to this. And so it's not slope. It's a little too generic. It's rate of change. Slope is rate of change, but you just got to throw the units in there. I love it.
One thing is, I don't know if we'd be able to draw conclusions about like whether it's worth waiting from this graph alone, because I would bet that a tree would probably grow slower as it matures. So you kind of have this like optimal point where you're harvesting based off of you're getting more volume per foot, but your foot per year is probably lowering as the tree gets older. So I bet if we had another graph, we could have an interesting problem there. But
yeah, in other words, does the tree grow like this, but then actually does it level off out there?
I was just looking that up, Felix.
No, I mean like the tree height, like because right now the volume based off of height is increasing, but the height over time as like a separate graph would be like kind of leveling off.
Yep. Height over time, because this is how you grow, right? You grow quickly at first, but then you kind of level off and you basically stay the same height for the rest of your life. And so, yeah, I mean, that's the point, is that this is complicated. This is cool. And this is why, you know, math can be made to lie, in the sense that you could draw a conclusion from this as though you understand the graph, but it's like you've only looked at the first 80 years of it. And like, what if it changes out there? And so, you know, you actually can make terrible decisions, even though you use math. Just because you get math in there doesn't mean you're right. Like, this is not simple. There's a lot of stuff to think about. So yeah, that's a very good point. Many things, Drew, and I don't know if you've ever been taught how graphs, like this part of it right here, is actually exponential. So animals and stuff will grow exponentially initially, and then maybe right in here somewhere they kind of stop that and then level off. This overall graph is actually called a logistic model. And it is one of the choices for regression on your graphing calculator. And so that's a real model for lots of how things work. Populations of animals do that. Like if you introduce oh, you guys froze again. Now you're back. Populations of fish, like you throw some fish you don't want in a lake, somebody, you know, fish gets loose in a lake and it's like a bad one or whatever. It'll grow exponentially, but it can't keep doing that, because sort of pretty soon fish will just be boiling up in the air and they're not even in the water anymore, right? So many things in nature will grow logistically. They'll grow really quickly, but then they'll level off at what's called the carrying capacity of the lake, you know, based on the food and the size of the lake and so forth. The population will kind of level off. And so, you know, it's no joke to choose an equation that actually models it. You got to have some experience to kind of choose it correctly, because you are getting paid to make, you know, major league predictions, if you will. So kind of cool. So there, you're a hair smarter than you were before. Let me show you another thing now. We've been studying product rule and quotient rule. And so I ran across something kind of cool that I think you might like. Some years ago, I ran across the Witch of Agnesi. What in the world is the Witch of Agnesi? There she is. There's the witch herself, Maria Agnesi. I might post these notes, because I'm not going to spend 30 minutes looking over this. But, you know, a part of what makes all education interesting is tying it to real people. And it's kind of interesting. And I found this in the article, but basically I just went to, I don't know, Google search or whatever, and I just found a bunch of interesting facts and put them all on a Word document here. And we'll dial this down to a calculus question in just a second. But there's an interesting story as to how this curve that she came up with back in, let's see, what year is this? I'm sure that's in here somewhere. She was born in 1718, whatever, 300 years ago. She came up with this, but she came up with a curve that none of you have seen before, and it's really kind of beautiful. And I said here, I typed this myself, can you see how this curve can be drawn geometrically? Let me zoom in on it a little bit. No photographs back in 1718. Somebody has to just draw a picture of you. Can you see how this curve is drawn? So first of all, notice this. There's a circle sitting here first. So you have an XY axis and you draw a circle sitting there. And then the height of the circle is whatever this A is in the equation. So let's just say it's 10. So this thing is 10 tall. So you have a circle of diameter 10. And then you draw these radial lines out. So let's just look at this one. You draw this line way out there first and you say, hey, look, see where it hits the circle? It hit the circle right there. And then you take off from there horizontally. And then you look at this line and you say, where does it hit that horizontal line at 10? Where does that hit? And then you go down from there, and where those horizontal line runs into the vertical line, like that's where it hits the graph. And so that's kind of beautiful. I mean, isn't it? Like if that curve right there that results from this, let's do it again really quick. What about this one over here? You draw it up here, hits the circle right there, and you take off horizontal. It keeps going, hits the line up top, drop down, hit that curve. So that geometry, that geometrical interpretation of this curve creates this really cool kind of bell-shaped looking curve. Now, all by itself, that's like kind of beautiful. I mean, who thinks of these things? I mean, it's kind of neat. But why is she famous for this? Well, look at the applications that I listed down below, many of which I don't understand. One of them is this graph called the Witch of Agnesi is used in spectroscopy from physics. Maybe you may remember that has something to do with light, and you look at light and there's a spectrum to it. So the word spectrum is where spectroscopy is. It basically has to do with if you look at light and you don't see all the colors, then stuff is missing. It starts to tell you what you're looking at. It's like, oh, that's magnesium because this is missing. And that's the gist of spectroscopy. Or this is one of probably more of my favorite one. This is used as a model for a bump-shaped disturbance in a fluid model of the atmosphere. And so let me oversimplify that by saying, okay, you got this particle of water, or something floating in the water, and it's just ripping along in the stream. But then it encounters something, like it encounters a calculator. Someone's left a calculator in the stream. That is weird. And so it has to go up over the top of it. Does that make sense? Probably a better way to think about this in terms of being practical is like what air particles do when an airplane wing hits them. So the air particle's just sitting there. Here comes the airplane, and it's forced to go up and over the top of the wing, and that process creates lift. And so a person might ask, I wonder how fast that particle's moving relative to the plane wing, and it's actually changing speeds as it gets over the top of the wing, which causes lift. And so speed is a calculus statement. And so, in the end, this curve wasn't just kind of cool looking piece of geometry. It actually, made a model of real things in the world. And so that's why she got famous for it. If she had just drawn a beautiful looking curve, nobody would know who she is because she would have just been a math nerd that came up with a cool shape. But what I want to do, and again, this is another example in statistics. If you've taken statistics, you might be familiar with that bell-shaped curve. Even if you hadn't, you probably heard that term before. And so this particular bell-shaped curve is not the same one that you study in statistics. It's slightly different, and it does a slightly better job of modeling some things that exist in the world. So this isn't just a beautiful curve, it's a cool application. Well, notice not only is it a geometrically built curve, but somebody even figured out, and I just find this amazing, somebody found an algebra equation for the same exact curve. And historically, there were people that thought geometry was awesome and it modeled things in nature, and there were people that liked algebra, and they actually fought, they hated each other. There was issues about who was better and so forth. But in the end, turns out they're the same thing. Like when you have an equation that you write down, there is a graph that comes from it that's geometry. And so, I kind of take that for granted, but you can write down any algebra equation you want that no one's ever seen before, and you can go into Desmos and it'll graph it. And you might be the first human that's ever seen it before. But it will create a geometric shape, and that can just be cool looking or maybe not. And we'll play with that in this class a little bit later. But they're kind of the same thing. Well, of course, what I'm asking this for is this particular equation. You should now be able to take the derivative of it, because maybe in this case, the derivative is the speed of that air particle going over the wing. And maybe we're going to design a new wing that makes flight better or something of that nature. And so, being able to find the derivative of this is either just beautiful because it's like, here's another curve, let's find its slope. Well, let's go play with this now. So again, I don't think I need to take a picture of that. I'll just write its equation. So notice the equation, y equals a cubed over a squared plus x squared. And notice a is a constant. Anytime you lose letters of the alphabet that are like A's, B's, and C's, this graph is what you get if you choose A. And notice y equals A is the top, like A is the diameter of this circle. So if I pick 10 for A, then this is going to be based off a circle that has a diameter of 10. So you're picking a number for that. So let's do that. Let's see if you, because of my brilliantly clear explanations from yesterday, let's see if you can take the derivative of this. Now that you know, well, 3 rules, the power rule, product rule, and quotient rule. So let me write the equation down. We'll say 10 cubed over 10 squared plus x squared. And there's no reason to leave that as a 10 cubed because that just looks confusing. I want to know, can you tell me y prime? Like there's a cool equation that exists in the world that happens to be Interesting. The Witch of Agnesi. Again, this is not simple. A fairly simple looking equation, but it's not that simple to take its derivative, but I did teach you how. Given that you have a graphing calculator and or Desmos, I've taught you some calculus, and so you should be able to come up with a derivative for this, but you might get it wrong, right? Because you're not that good at it yet. I haven't taught you very much. But I just wonder rhetorically, could you get out Desmos and cheat to find, say, the derivative of that at x is 3, and then plug it into your equation and realize, hey, look, it's the same, I got it right, or it isn't the same, I must have done something wrong. Like, you don't need me to tell you got it right or wrong. I've just illustrated today with 2 problems that there's a whole world of questions out there that you've never considered. And that's the way, if this ever shows up in life, it's going to show up like that in a way you've never considered. And so you're going to have to check yourself. There'll be nobody there but you. Here's a couple of things. Can you move the x squared to the top so that it's x to the -2? And then you can just use power rule. Can you do that? Well, I've already told you, no, you can't. Do you understand why?
Wouldn't it still be like an addition between 1,000 and x to the -2?
Yeah, maybe it's an addition. Is that okay? Answer is no. That's because right now isn't x squared being added to 100? And so you can't get rid of that by essentially a multiplication operation. When you're moving it from the top to the bottom, that's a multiplication operation. So I wish that were true, because that would make this problem easier. Or perhaps you thought, I'll just cancel the 100 and the 1,000 so that I end up with 10 on top and x squared on the bottom. You should more know that that's not true, because you're screwing up the distributive law. But it's like there's some things you could try to do to this algebraically to get it to be a little nicer. But you can probably appreciate that if that was possible, wouldn't Maria have already done it? Like, wouldn't she have canceled the a cubed over a squared and just said it's a over x squared? Why would she give such a dumb explanation for it? Like, you can't do that. There's just a lot of deep magic to algebra. Like, none of these things are possible. Like, you're stuck. It is what it is. You can't do anything to this. You got to take the derivative of it sitting there right now. Therefore, which rule do you need?
Quotient.
Yeah, it's junk divided by junk. You're going to need the quotient rule. So let's see if we can use it. I gave you a minute to try it. So I guess you could say that that's our u, and all of this together down here is our v. And I'm reminding myself that the quotient rule, let's see, is, I kind of have it memorized, is u prime v, u v prime. That's how I remember it. But then it's a minus sign, and then it's over v squared. So that's the quotient rule. You got a note sheet for it. So let's see, what would y prime be then? Well, I'd be taking u prime, looking back up here at the top. What's the derivative of 1,000?
0.
0. Derivative of a constant is 0. So that's kind of cool, because that'll make my problem a little easier. So it's u times v. So I'm writing 0 times 100 plus x squared, which of course is a waste of time because I'm multiplying it by 0 anyway. But I would at least like to see it written out.
Did he freeze? Oh, you're back. Okay.
I was going to say, I was looking up at you guys and you were all like, oh, they froze again. So there's u prime v, and then minus u's 1,000. And then what's v prime? What's 100 plus x squared? What's the derivative of that?
2x.
Yeah, the derivative of 100 is nothing. And the derivative of x squared is 2x. And I'm just writing everything out just so that you can see it. And then what goes on the bottom will just be squared. So that'd be 100 plus x squared squared. And you should understand that that does not mean 100 squared and x squared. That means parenthesis times parenthesis, distributive law. Should I distribute that out? The answer is absolutely not, because the only reason I'm doing this is to use it for something. And if I distribute it out, there's going to be x's everywhere. Like in a minute, I'm going to plug in x is 3 or x is 7 to find a slope. And it'd be way easier to plug it in just like it sits. But I don't want to plug it in now because there's a lot of ugly here. So let's see, I got 0 times all that, that's gone. And then 1,000 times 0, that's gone. I just really have negative 1,000 times 2x. So I have negative 2,000x on the top and 100 plus x squared squared on the bottom.
Is you lagging really bad for anybody else?
Say that again, Eve.
Yeah. I'm here.
You're lagging so bad I can't hear half of the stuff you're saying.
Let me try. God, this is frustrating. I sure apologize. I don't know. Let me see if I can leave the meeting and come back again, if that makes any difference. I don't know if I can leave the meeting as the host without ending it. So I'm a little.
You can. Someone else ends up being the host.
I don't want to say end. How much is it going in and out? Is it like constantly, or is it like there's a little batch of it and then nothing?
So a little batch of it and then nothing. Like right now you're fine, but like sometimes it does go in and out quite a bit.
Okay. I don't know. I guess I'll just talk slow. We'll have to just muddle through it. We only have another 30 minutes, so. Sure apologize. So let me share my screen again. If that happens and I don't notice it too, please interrupt and say, we just missed the last 2 minutes of what you said, and interrupt and tell me that. So let's see, let's go into Desmos. And let's graph the which of Agnesi using 10. So divided by 100 plus x squared. So notice, wow, that's amazing. I mean, you should kind of think that's incredible. It works. That's cool. Like there's the circle sitting in there and everything. And so what if I said, what's the slope of that? Now, again, in the real world, you don't just get a slope equation and go, yay, like you use it. You go on from there. And so we want to know the slope at, say, 4. Well, you should be able to look at that and predict. And notice this graph isn't screwed up in terms of its scale. So you can count on x is 4 giving you what you would see. So do you see that and go, yeah, that looks like negative and not very steep, like maybe -0.5 or something like that? Does that look reasonable? So you're sitting here checking your work. So now we have a physical prediction behind what to think we're going to get for y prime of 4. And you should be able to do a lot of this in your head, like negative 2,000 times 4 is negative 8,000. And if x is 4, 4 squared is 16. So the bottom you have 116 squared. So I'm basically sitting here thinking, I sure hope that comes out like a negative a half or something. And at least I can see for sure now it's negative. And oh yeah, 0.59. So I get a really crazy decimal, but I'm just going to round it off and say it's about negative 0.59. So that looks right. And so you see, I'm checking my work like that seems to fit, makes sense. And as I said, if this was not just graphing and playing around and practicing, but this was actually the speed, then that would be telling me how fast that particle is moving over the airplane wing or whatever. And then that'd be interesting. I'd be using it for something. And so just kind of a cool equation, but as an example of like what you should know, how you should be able to use, say, the quotient rule, recognize it. That's kind of a cool application. I don't think the assignment is terribly hard. You never want to trust a math teacher who says stuff like that, but you have time to either ask me right now about some questions that maybe you tried in the assignment, or maybe you ask me them after class. I don't know which, but I want the assignment to be relatively straightforward in my open math. The test questions I give, I want to be relatively straightforward. But that's cool practice. Notice it's working. Quotient rule is in play. Allowed me to get the answer to this.
So in this situation, 4 represents the distance from the x down, and then the negative 0.59 is the distance of
Yeah, 4 is really just the x coordinate. And in this case, notice I'm cheating to get the same answer that we discussed a minute ago. But if I say, what's f prime of 4? Notice I didn't have to know calculus to use that cool piece of technology to check my work, but it's literally telling me the slope of the line at x is 4. So again, just to make sure the notes are kind of good, so you don't have to watch the whole dumb video after this, I'll throw this into the notes. So if we're saying, hey, we went here to x is 4 puts me right there on the graph, and we're saying the slope of that line maybe right through there, that slope. And you should again be able to go one step further with this, right, and actually find the equation of that line. And you're doing that, you're going to definitely do that on a test. You're doing it on my quiz. You're doing it in your assignments. I haven't practiced that with you a bunch because I've got to spend some time teaching you calculus, but you should be able to find the equation for that line. Feel free to stay after class and ask me about that on top of just draw it in there. So it's like, hey, cool, I found the slope of the curve. Notice right up here, that's kind of interesting. Like apparently at 0, the slope is 0. You should be able to look at that equation right there and say, yeah, if you put 0 in for that, you'd end up with 0 over 100 squared. That'd be 0. So that's working. Slope is 0 when x is 0. Notice all the slopes over on this side are positive. In other words, if you put a negative x in, you're always going to get a positive slope. Hey, yeah, look, that makes sense. If I put a negative x in there, then I'd be multiplying it by negative 2,000, and then it'd be a positive number. And so that kind of makes sense. Okay. Goodbye. Quotient rule, product rule. You need practice, but you now know those. So now we will turn our attention for the remaining 25 minutes or so, and then all day tomorrow to 3.5. So we're on 3.5. Yeah, 3.5, which is actually a really cool question, which is, what about trig? Keep in mind what we're doing in calculus, which is sort of a stupid way to do it, is to say, hey, derivatives are cool. They tell us the slopes of curves. And so because that's cool, then let's go find the slope of every curve. So it's natural that if that's the approach you're taking, to say, well, what about trig functions? Like those sine and cosine and stuff, those have slopes. What about logarithm? Like we're just going to look at all of them. And so now we're going to launch into trigonometry. And I want to give you a chance to understand this really deeply and really cool. First of all, let's go back to Desmos and remind ourselves what the graph of, let's see, maybe I'll type f of x in case I decide to use it again instead of y. But let's remind ourselves what y equals the sine of x looks like. So you should go, yeah, that's right, sine wave. But you may remember from 112, and a big chunk of what I'm going to do for the next, I don't know, couple of days. I just saw you guys all freeze again. I stop talking when I see you guys freeze. A big chunk of this is you need to go get your trig knowledge back because you had it at one point to some level, and now it's probably gone-ish. Like, I doubt you remembered. I mean, I'm sure you remembered like, oh yeah, it's a sine wave, and that's what that's generically called. But do you remember specifically that it starts at 0, 0? Whereas cosine?
We lost all of that.
Yeah, I saw you guys freeze. When I see you, I'm looking at you when I'm talking, so when I see you freeze, I'm not talking. So let's look at this and let's think about what the sine of this, or what the slope of this graph is doing. Like, stare at it for a second. So I'm going to go over here and do what I've done before, which is graph a point where I stick an a in there, and all of a sudden I'm glad that I thought to call that f of x, because now I can say f of a, and it'll graph this point for me, right? So, you know, like, what's the slope right there? You should be good now at saying, hey, positive number, but not very big. Of course, that's very interesting, right? The slope right there is what?
0.
1.
Yeah, 0. And then all through here, the slope is negative, right? And then the slope is 0 again. That's like, there's a lot of places with the slope of 0, right? So let's think about that. So I'm going to copy this into our notes so that we can. So what I want to do is use what we learned, and this is why some books teach what we learned in section 3.2, which was looking at how the graphs compare. Like, if you have an original function and then you also have its graph, like how they compare, we're going to use that to figure out the answer to what the derivative of the sine would be. And again, I already gave you the cheat sheet. I would recommend, to Felix's point the other day, like, don't look at that, at least as far as the future, because it's going to take away some of the joy of discovery, if you will. And I would also, you know, I guess, like you to consider that some of you don't care. Just tell me what the derivative is and let's get on with it. That's okay to think that, but it also kind of takes part of the fun out of it. So we have this f of x graph, and what I want to look at now is, you know, what would, if f of x equals sine of x, then what would f prime of x be? What would its slope be? And notice we are in no position to even have anything to figure this out. Like, that's not quotient rule. That's not power rule. It's not product rule. It's like, man, this must be some completely different animal. And so all I'm really doing is playing with it with tools that you have. In other words, would you agree, as we said a second ago, that the slope of this curve is 0 and 0 and 0 and 0? So if I consider the graph we're after, so let's at least go try to kind of look at what the graph of the slope would look like. Remember, the f prime graph tells you, the y coordinate of it tells you the slope on the original graph. In other words, our f of x graph is going to have to cross the x-axis in every one of those places. Does that make sense? Since all of those are slopes of 0. And then think about this. I alluded to this a second ago, but what do you notice about these slopes from here to here? What are they? They're all what?
Positive.
They're all positive. So does it make sense the graph here has got to be, you know, positive. It's got to be up here somewhere. I don't know what it looks like yet. But then also let's even stare a little closer at what that slope actually is. Would you agree that down here the slope is 0, but then it gets steeper? It gets steeper as it goes up. Do you agree with that? And would you agree with me that the slope is probably steepest about right there? What does it look like that slope is right there, would you say?
I guess it's the same point as 0, but it looks like it's 1, I think.
I think you're right. I think it looks like it's about 1, doesn't it? Like here's up 1 and over 1. So there's 1. And doesn't it look like it's about 1? And so in the end, what's really happening is, as far as the green graph is concerned, the slope is 0 here, but then it starts getting bigger and then it maxes out at 1 and then it goes back down to 0 again, doesn't it? Isn't that what the graph of f prime of x would have to look like?
This is kind of looking like the cosine wave.
Let's keep going with this. Eva's saying this is kind of looking like a sine wave or a cosine wave. Well, over here, isn't the same thing happening? Aren't all these slopes negative? And don't they reach a maximum right there of about -1? And so it's kind of like that pattern just continues. Like they max out at -1 right there. Like notice how this looks like a sine wave or a cosine wave. Let's move it over a little bit further. So over here, it's actually going to there. And here, right there, its slope is also 1. So maybe I don't know exactly what that green graph is, but that's definitely it. And this, whether you're tracking with me, is whether or not you understood section 3.2 right now. Like apparently that's the graph of the derivative. And so the question is, do you recognize it? And Eva's saying, isn't that a cosine graph? Is she right?
Yes.
Yeah.
She is right. So, man, it sure appears that if f of x equals the sine of x, that f prime of x is equal to the cosine of x. And that's what it says on my note sheet. That's actually true. That's exactly what it is. Crazy. So it's almost like, you know, the way to find the slope in trig land is to use trig to find it, which is kind of, you know, not obvious, isn't it? I mean, isn't that kind of cool? It's surprising, if you will. So of course that means something like, I wonder what the slope of the sine curve is at, say, 1 radian. And you say, well, I'll just take the cosine of 1 radian and I'll know. Apparently, like that's what it's saying. I mean, so that's true. That's just kind of cool, kind of surprising. What I gave you there is kind of an intuitive understanding of how that works. So let's just try this out on your calculator real quick, just to give you time to soak on this a little bit. Like if I go to x is 1 on the sine graph, I'm right there. And notice that looks like a small positive slope. And so now bust out your calculator in radian mode and say, okay, well, to find that, I take the cosine apparently. So f prime of 1 would be the cosine of 1. I bust out my calculator, I type cosine of 1, and sure enough, it says 0.54 is the slope. And I look at the graph and I go, yeah, that actually looks pretty reasonable. So, you know, we're talking about that line right there. And sure enough, the cosine of 1 is approximately positive 0.54. It's like, that actually kind of looks right, doesn't it? Now, let me show you something. I'm going to make I guess we'll call this a sales pitch. This is a sales pitch for Math 253 in the spring term, which many of you do not need for your degree. And so I won't see many of you. But let me show you one of the things that's really cool about it. If you have time in your schedule, even if you don't need it, this is really neat. I got a degree in math to teach math, and I never had to take this class. And therefore, I never understood it until recently in my math life. I taught it last spring for the first time, and I never had taken it before. So I didn't really understand it. So I had to teach it to myself and then teach it to the students. And it's like, God, it's amazing. Let me show you something that's true. Turns out that the sine of x is equal to x, let's see, I forgot the word, minus x cubed plus x to the 5th minus x to the 7th, and so on and so forth. Notice the signs alternate, and then the powers of the x are always odd numbers. So the next one will be plus x to the 9th minus x to the 11th, and so forth. we're not quite done. What else goes here? Well, a 3 goes down here. That's why I left room for it. A 5 goes down there, a 7 goes down there. And notice the dot, dot, dot is this goes forever, never stops. That's why it's in a calculus class. And then we're still not done. There's one more thing. This is not just a 3. It's 3 factorial, 5 factorial, 7 factorials. Anybody know what factorial means in math? Like in English, it means not 7, but 7. What's
A number multiplied by all counting numbers previous to it.
Yeah. If you took statistics or some class that involved probability, this comes up. And so 3 factorial means 3 times 2 times 1. 5 factorial means 5 times 4 times 3 times 2 times 1. And there is a button for that in your calculator, but we won't go into that now. And so this is something called an infinite series, and that's what you study in Math 253. Now, what's amazing about this is infinite series is literally sign can be rewritten as well. Isn't that just a polynomial? Like that's x cubed over a number. That's x to the 5th over a number. Isn't that just a polynomial? Like those are cool. Those are easy. Like those are easy to work with. Those are easy derivatives to take. And similarly, it turns out that the cosine of x is equal to, well, not all the odd numbers, but all the even numbers. And so you end up with x squared over 2 factorial, and then plus x to the 4th over 4 factorial, and then minus x to the 6th over 6 factorial, and so on and so forth forever. And so you'll learn like why that is. That seems like totally from left field magic. You've never heard of that. I'd never heard of it. But it's a really cool feature, and you haven't thought about this, but you know, a second ago we all just took the sine of 1, right? And you just took it for granted. Hey, I paid $100 for this thing. It should tell me answers like that. The only reason this exists is because somebody discovered that. There'd be no calculator. Like sine of 1 is the opposite over the hypotenuse in a right triangle. How would a calculator just know that? And you might notice that it's not just stored in there, because you don't have to take the sine of 1. You could take the sine of 1.3296447, like type this huge long number that seems to know the answer. That's because some math person figured out that sine can be rewritten as a polynomial like this. And so when you say the sine of 1, it's actually plugging 1 into that statement. It's going 1 plus 1 minus 1 cubed over 6 plus 1 to the 5th over 5 times 4 times 3 times 2 times 1. What is that, 24? I can't remember. It's not 24, it's 120. If you type that into your calculator, if you try out that little blue sequence, you'll get the same answer as the sine of 1 a second ago. And that's why your calculator exists. You wouldn't have one if it wasn't for this. So this is cool stuff. Like we've been using it and you didn't even know it. You've been using calculus in your Math 112 class and you didn't know it. And oftentimes that's calculus's real application, is somebody has built something as a result of it and you're benefiting from it, but you just don't know it. Well,
if it goes on forever, how does it come to a final answer?
Good
or
question.
Is that a 2-3?
It's an approximation, because when you get way out there, does it make sense like x to the 20th over 20 factorial? Well, think about what's on the bottom of that. 20 times 19 times 18 times 17. The number on the bottom is just massive. And so if you had 1 to the 20th over that giant number, it's pretty much 0. And so this is why it's in calculus, is again, we're talking about something that's approaching a limit. Like you only have to go out about 8 terms and it's close enough. Does that make sense? That's a wonderful question.
Yeah.
Now, what I'd like you to do is watch, I guess just watch me do this, but let's take the derivative of sine, except we're going to take the derivative of, well, sine in this form. And we love that equation because that's a polynomial, and power rule is the easiest rule we have. And so that's not a hard derivative to take. Do you agree with that? We love the plus signs. I'm sure glad that wasn't x times x cubed over 3, because then it would be the product rule, or x divided by x cubed, then it'd be the quotient rule. But this is just a bunch of plus signs and a bunch of exponents. This is a polynomial. This is really easy with the power rule. Let's take the derivative of the sine of x. Well, you tell me, what's the derivative of x?
1.
1. What's the derivative of x cubed?
Wouldn't it be 3?
3. And what else? Not just 3.
3 to the x to the 2nd.
Yeah, and notice the constant just comes along for the ride. In other words, really that's just a 6 down there, right? 3 times 2 times 1, it's just a 6. So it's like, now it's 3/6. What about x to the 5th? What's the derivative of x to the 5th?
5x to the 4th.
Nice job, 5x to the 4th. And then there's just a 5 factorial sitting down there. And so x to the 7th would be 7x to the 6th over 7 factorial. Do you see where I'm going with this? But isn't 3 factorial 3 times 2 times 1? I'm just writing it out so that you can see it. And isn't 5 factorial 5 times 4 times 3 times 2 times 1 and 7 factorial? What do you notice about that?
Why doesn't it, if the derivative of sine is cosine, why doesn't it look the same as cosine?
Yeah, why doesn't it look the same as cosine if they're the same? Well, we're still simplifying this.
Well, don't you remove the 3's cancel out and leaves you with 2 times 1?
Yeah, doesn't this 3 cancel with this 3? Leaving 2 times 1 down there, and doesn't this 5 cancel with that 5 and that 7 cancel with this 7?
Now it looks like the cosine.
Now it looks like the cosine. So you have 1, and then you have x squared over 2 times 1, but isn't 2 times 1 2 factorial? And then you have x to the 4th, but it's over this, but isn't that just 4 factorial? Oh my gosh, it does look like cosine. Like this is, if you will, more of like a proof, a mathematical proof. It wasn't enough. I don't know if this occurred to you, but back here, you know, how did I know that that curve, the green curve, was actually a cosine wave? It just kind of looks like it, but what if it wasn't quite, what if it, you know, wasn't the same exact curve? I mean, there's nothing saying it couldn't have, for instance, I'll erase this, but there's nothing saying it couldn't have got there this way, right? So still all negative, like I don't know that for sure. So it's, I gave you, you know, first just an intuitive guess that it looked like cosine, but thanks to calculus that you haven't learned yet, this is actually a proof, if you will. Wow, it is the cosine.
So because all the fractions are separated by addition and subtraction, we don't use the quotient rule.
Yeah, we love the plus. We love the plus sign. So the pluses and minus signs, we can do them all separately. And then the number on the bottom is just a number. If that had down there had been like an x, then we'd have to do the quotient rule, but it's just a number down there. In other words, you can think of x squared over 3 factorial is really just 1/6 x squared. In other words, it's just a constant multiplied by it. Does that make sense? Let me show you just one other thing since we're well, I'll just show you this really quick. Like what if you had x cubed over 7 and you said, hey, I think that's a quotient rule problem? Then good, do it with the quotient rule. What's the quotient rule say? Quotient rule says derivative of the top times the bottom left alone minus the derivative of the bottom times the top left alone. Isn't this true? All divided by what?
Could you add parentheses so we know, just for visual?
Sure. In other words, this is u prime times v, and this is v prime times u. Does that help? What's the rest of the quotient rule?
V squared.
V squared. So down here is a 49. So what's left as a result of that? Well, this term goes away because of the 0, right? 0 times x cubed is 0. So then I have 3x squared times 7 over 49. Well, doesn't this 7 cancel with one of the 7? So you get 3x squared over 7. So yeah, it is quotient rule. However, you could look at this as just 1/7 times x cubed and think of the 1/7 as just a constant out in front that you're multiplying it by, right? And don't we always say, oh yeah, look, the 3 multiplies by the constant, that's 3/7. And then that goes down to x to the 2nd. So it's like, yeah, same thing. The constant comes along for the ride. And so we're going to probably do our problems in class this way, just because it's faster. We're going to see these little shortcuts, but it's like, if you see junk divided by junk, it's quotient rule. If it bugs you, then do the quotient rule.
I see it
They
now.
work out the same anyway. And that's
Okay.
a wonderful question. I didn't say that to the 8 o'clock class because nobody asked such a good question. So good for you. Let's look at one more thing really quick before we run out of time. There's cosine. So now our question is, like what's the derivative of cosine of x? And notice it's still like both cosine and sine are the same graph. They're like moved a little bit left and right, but they're sine waves. If I took which I think I can do, I don't remember how exactly, but if I turn the grid off and turn the axis off, and it's like that's a sine wave. Does that make sense? Like you just collectively call it a sine wave. Now I don't know how to turn it back on because I never do that. But does it make sense that the derivative of that, just like the derivative of sine was cosine, well, this is kind of going to be the same thing. Well, let's stare at this a second. What would its derivative look like? I'm going to copy this over to our notes so I can play again. So what if f of x equals the cosine of x? What would f prime of x equal? So of course we need to know the derivative of all the different functions, not just sine. So let's bring that dude in and let's kind of analyze it in the same way we just did a second ago. Let's crop that dude down. Draw that baby over there, make it all big like, oh yeah. So do this in blue. What's f prime of x? Like what's its graph look like? Well, again, isn't the slope 0 right there? It's 0 right there, 0 right there, 0 right there. And then let's see, between those points, what's the slope here? Well, isn't it negative there? So isn't it going to do this? And then between here and here, isn't the slope positive? So that means it's going to do this. And so, yeah, kind of like last time, I get like a sine wave or a cosine wave or something. But what is that specifically?
This isn't quite a sine wave though, right? Because a sine wave goes up first. So it's like, it's a negative sine wave.
Yeah, look at that excitement, man. If you could moonwalk, you'd be doing it. I love it. Yes. Notice Eve has some knowledge that maybe some of you have lost. Like, what does sine look like? Actually, sine took off from here and went up. That's actually what sine looks like. But from your Math 111 class, what do you have to do to a graph to get it to flip over? Because it's like the same thing, but it's like flipped upside down. And Eve said it, but like to give everybody else time to catch up. What do you do to get it over? Yeah, doesn't it make it negative? Like parabola, if this is y equals x squared, then y equals negative x squared went upside down, right? I mean, that's all you got to do. And so, oh man, that is rad. So apparently, oh, that was awesome, Eve. Apparently, it's actually negative sine of x. Oh my gosh, that's really cool. High five. Can I high five you via Zoom? That was awesome. Like this is cool stuff. Like if you don't, it's just like fun to figure things out. You should be excited. You're doing something wrong. We don't have time to do this, but just think about this for a second. If we went back and took the derivative of the red cosine graph, then apparently we're going to get sine, right? Except for what's going to happen. Well, all the signs would be backwards. Does that make sense? Like this is a plus sign. Well, I guess it'd come out as a negative sign. And this would come out as a plus sign, and this would come out as a negative sign. That's what would happen if we took the derivative of this red graph. I would encourage you to do that and kind of prove that it really is negative sign. It looks like it's negative sign. I mean, that's just amazing. I mean, this is just super cool stuff. Keep in mind, like there's no guarantee there's no guarantee that there's always some equation that will tell you the derivative. So the fact that we found one for sine is like, oh my God, that's amazing. I can't believe there's an answer to this. And not only that, it's almost like, it was his uncle or something. It's like one of his cousins. It's just kind of cool. If you're not excited, you're doing it wrong. This is neat. So there's your first two pieces of information that you need to know. You need to know the derivative of sine is cosine. You need to know the derivative of cosine is negative sine. Now you'll probably have that memorized before this class is over because it's going to come up a lot. But you have my note sheet and it tells you that. What's our next question going to be then?
I'm assuming tangent or tan.
Yeah. What about all the other trig functions? Remember there's a tangent and secant and cosecant and all that. Well, we'll tackle those tomorrow, but I'm gonna have you build those. Like you don't need me to tell you. Now that you know sine and cosine, you'll be able to build the other ones yourself. I'm actually gonna put you in breakout rooms and assign like 4 of you to figure out tangent and 4 of you to figure out cosine. And what would be really cool is if you could actually, collectively write something and then share it with everybody. But unless you have an iPad, then you can't write like I'm writing. And so there's not an easy way to do this. So that's a bummer, but you can actually make them yourself. You need to know 0 new things to make all the other 4 trig functions. So we'll tackle that tomorrow. But let me show you one thing really quickly. Unshare. Fail. It was a failure to share. So just a reminder, in my open math, I showed you yesterday or the day before yesterday in course out information, there was the notes. And so that actually tells you the trig, that tells you the derivative of sine is cosine. It even tells you tangent and all that stuff. I'd encourage you, don't cut your own joy. Like don't look at that if you can help it. But right here, basic trig identities, like we're now looking at trig, and my guess is your pre-calculus teacher, your trig teacher, gave you some sheet that looks like this. And so if they gave you a good one and pull it and you looked at it a lot, then get that one back and use that one. But this one's got everything you need. You might want to review some of these things because now that we're doing trig, we're gonna, the kind of questions you'll have is like, f of x equals sine. And so can you tell me the slope of that curve at pi over 3? And so what's going to happen is most calculus was invented long before we had calculators. So nobody knew what the sine of 1 is. Does that make sense? Because like Martin pointed out, it is an approximation. So nobody knew what the sine of 1 is. But all these exact ones, you may remember from Math 112, these are ones that you can actually get exactly correct. These are the only angles that you can get exactly correct. And so in your calculus class, every time they ever ask you for a slope, it's always going to be at pi over 4. Or pi over 3, or 4 pi over 3. They'll never say pi over 5. It'll always be something you can answer exactly, which is sort of lame because the real world isn't stuck to just these angles. I think that's kind of dumb, but you're going to need to give exact answers. Does that make sense? So let's just remind ourselves of one quick thing. I see I'm over time here, but there's like, we're going to need this tomorrow. Tangent is sine over cosine, cotangent is cosine over sine. We're going to need that directly tomorrow. But as an example, do you remember how to read this chart? In other words, if somebody says, hey, what's the sine of 4 pi over 3? Can you read that off this circle right here? Is sine the x or the y coordinate?
The y. The
Sine
y.
is the y. So if you're asked for the sine of 4 pi over 3, you say, oh, look, there's the point, and sine is the y coordinate. So there it is. It's negative square root of 3 over 2. It's not that you can't bust your calculator out and say sine of 4 pi over 3, but it's going to give you the decimal equivalent of square root of 3 over 2, and you're not going to recognize that. And if my open math wants it exact, then you're going to get it wrong. And so, like get your trig knowledge back is what I'm saying. Stare at this a little bit. You're more than welcome to ask me too on the fly, but take a look at this chart and be able to read it again, because if we're going to find the slope of tangent, we're going to have to look at this to get it. We're gonna have to be able to read our info off of that. There's some identities in here that we'll need very occasionally, not very often. We won't need this stuff very much, but we will need it from time to time. And there's like the law of sines and the law of cosines. We're gonna need that a bunch in this class later on. Won't need a lot of this stuff in here, but quadratic formula, little hint, you should be using that for that project that's due Monday. If you're not using the quadratic formula, you haven't taken that as far as you need to just yet. Some other cool things in here, but anyway, just refamiliarize yourself with some of this, because so that you can stay your focus on calculus and not be like, oh my gosh, I forgot all my algebra. So, and also if you have some curiosity left in you based on the fact that tangent is equal to sine over cosine, could you like go figure out the derivative of tangent yourself? Do you need anybody to tell you that? Like, try it. Even if you get it wrong, at least what we do tomorrow will be like, oh, I see. That's cool. All right. As usual, 5 minutes over, as it will be almost every day. And get yourself out of here. Stay after if you want to ask any questions. I'm going to eat some cheese.
So we'll have access to all the trig identities on the test, right? Like,
Yeah.
I took the derivative of tangent of x, and I got cosine squared x plus sine squared x, and I know that's one of the identities. I just don't remember which, but we'll have that
Yep.
on the test, right?
Yep.
Okay.
Yep. All notes you always have on tests.
Sweet.
Math is not about memorization. It's about thinking.
Yep.
I had a question, and it was about the quiz.
Yep.
So, is it okay for me to just like blurt out like what I'm doing and stuff?
It sure is. Let me share a screen so I can write down what you say.
It's for 3.1. It's the first question. So like for the f of x minus f of a over x minus a, I understand that it's the same as f x plus h minus f of x, but for some reason I always kind of like once I like foil it, like once I start to build the equation, that's kind of when my brain stops. So I got 2x squared minus 4x plus 5 minus 5 over x minus 5.
Not over x minus 5.
X what was that?
That's where you're going wrong. It's not over x minus 5.
It's over.
Why not?
Oh, why isn't it x over 5?
Yeah, why isn't it x minus, why isn't it x minus 5? I'm saying that's not true.
Okay.
Let me show you really quick. So I'll make up, well, no, I'll go ahead and do what you're doing. Like this is the point 2. X is 2. And when you plug in 2 into the equation, you get 5 out.
Right.
And then you go to this other point up here somewhere, which is f of x. I'm sorry, it's x minus x. It's x and then f of x, because we're not limiting ourselves yet to what the point actually is. Do you agree with that, Andrea? And so then what do you do to find slope when you have 2 points?
The y2 minus y1 equals x, and then or m times x minus x1 minus x2, or x2 minus x1, sorry.
Yeah, in other words, you go f of x minus 5, because that's y minus y, like I wrote.
Right.
And then what do you do? This is where you screwed up. What do you do with?
So it's actually x minus 2.
There you
go. Duh, because you're not. Oh, duh.
So you went y minus y over x minus y instead of y minus y over x minus x, which again,
yes. Okay.
the dumb and understandable mistake, right?
No, okay, that makes. Yes, absolutely.
So in your case, because you wrote it down wrong, then things didn't simplify out and beautiful things didn't happen. But if you fix that.
Oh, yes. Okay, yeah. Because then after that, I got like x squared to the second power minus 4x over x plus 5. I mean, x minus 5. And then, I tried to take 2x out of that. And then I just got left with x minus 2. And then I was like, oh, like, I don't know what to do after that. But I felt like there was some, I felt like, I knew there was something wrong, but I don't know where I went wrong. And it's just because I messed up the f of a instead of just putting an a.
I was about to say, you just got excited. That's exciting.
I think, yeah, I think I did. I also, so for C on number 1, I did, you know what, that probably makes, okay. So I did y minus 4 equals 4 times x minus 2. Can you just, am I on the right path, or did I mess up right there?
Would you say y minus 4 equals what?
Equals 4 x minus 8. Sorry, the total, that was a,
Yeah,
actually
like before you multiplied it out.
yeah.
Yeah, in other words, this is kind of like slope.
Mm-hmm.
So the slope goes here, and if I was to divide x minus 2 to the other side, you'd have 4 equals y minus 4 over x minus 2.
Mm-hmm.
So slope equals y minus y over x minus x, and so you just rewrote it. This is sometimes called the slope. What's this called? The slope, point slope form or something.
Yes.
So like that's your y and that's your x, and so yeah. And then of course, check it yourself. In other words, the original function is 2x squared minus 4x plus 5. Like go graph that parabola,
Mm-hmm.
and then you get done here and you get your line. And you know it's nicest looking if you do what you said, which is distribute that 4 in there, and then maybe add 4 to both sides. So now you have y equals whatever 4x minus 19 or whatever the heck it is, and then graph it along with your parabola. And what you should see is, look at that. You know, it hits right there at the point 2,5. It hits right there at the point 2,5, and it really does look perfectly tangent. If you graph it and it looks like this, it's like, oh, that's not tangent. Or if you graph it and it's like, oh, it doesn't even hit it at all. Or if you graph it and it's like, going, it's like it should be hitting it tangent. So you can like graph it to kind of say, ah, sweet, I got it right. Like make sure there's a physical reality behind what you're doing, that you're not just going like step 1, step 2, step 3. Graph it. Step 3. Wonderful question.
And on Desmos, to make the tangent line like appear on the graph, do I just click that little like the blue like side squiggly little circle that shows up in the corner? Because sometimes my tangent line, when I plug it in Desmos, like I can get the f of x function to show up, but then when I try to do my tangent line, I type it in, but it doesn't like appear on my Desmos. So I'm not sure if maybe I'm just like not pressing like a button or clicking something that I'm supposed to.
Yeah, let's stare at that. It could be that your line is so wrong that it's just off the screen. Does that make sense?
Yeah.
It could be there and you just can't see it because it's so off. That could easily happen. So like there's my parabola. And you're right. See that little purple box? If I hit that purple, it turns it off. It doesn't get rid of it, it turns it off. And so that's possible. But it assumes that you want to turn it on. So in other words, when I'm saying I'm over here graphing y equals, I'm pretending I'm checking my work, like y equals x minus 2. See, it's like it wants to be turned on. So it's probably turned on unless you touched it. Now that I graph this, I'm like, oh, I got that wrong. That's not tangent to the curve.
Okay.
So the only thing I would say is like probably zoom out a little bit, because maybe the line's there. Let me give you an example. Like if I said y equals not x minus 2, but x minus 20, or even worse, x minus 50. Like, where's the graph? What's wrong with this thing? It's broken. No, it's not broken. Minus 50. Way down there. Like, zoom out some, because maybe you did a job that you're not even close. You know what I'm saying?
Right. Okay. Okay, that helps. Cool. And I think those are all my questions for now.
Yeah, that's more tomorrow.
We'll most likely have some later.
Yeah, anytime. Go try that. Talk more tomorrow. I learned stuff.
Awesome. Thank you for your help.
Yeah. See you tomorrow.
See you tomorrow.
Who else?
I had trouble on number 7 for 3.4.
Okay.
So the question went f of x equals, and then the numerator. Oh, I'll give you some time to.
Yep, go ahead.
Okay, so the numerator was just 7x squared plus 5x plus 5 over the square root of x. And so I was going, I had tried to put that into quotient, the quotient rule.
Yep.
And I got the answer wrong.
Talk me through it. So what you did.
Okay, let me go back to the page then.
It'd be better if I could watch you do it, but I can do what you tell me to do, and then at least we can both look at it.
Yeah, I wish you being in your class made me want to buy an iPad. So
I know, cool.
not a good thing for me. Okay, so I don't know why I didn't show my work. Hold on. That's
Doug, just real quick, like, could you switch this to a multiplication?
Uh-huh.
Okay.
Yep. In other words, and I think it's better to practice it as it is, but if you move that x to the 1/2 up to the top, and then to move up there, x to the 1/2 would become x to the negative 1/2, then you can think of it as big junk times junk. So now it's a product rule question. So that's totally true. It actually doesn't make it any easier, but
Of course not.
some things do.
okay. Well, I guess I didn't show my work, which I don't know.
That's
where
okay. Let's do it from scratch.
Sorry, what?
Let's do this problem from scratch. Like, tell me what I should do. I just reminded you over here.
Yeah.
What the quotient rule is. So you tell me what to write.
So plus 5 times the square root of x.
I agree.
And then you just from u just normally, and then the square root would be x to the 1/2.
Yeah. Brad, how did you do that, Cody? Cody wrote on the screen. Can you see that, blue? I don't even know how. I didn't know you guys could do that. Are you just writing on it with your mouse?
Yeah, I'm just writing with my mouse.
I didn't realize you guys had access to that. That's pretty powerful.
Yeah, we started becoming like real pros in Zoom, at least with my physics and calc class. Just yeah, we've been practicing a lot.
Well, I knew I could share a whiteboard, but then you write with your mouse, and it's really hard to write with a mouse. But I didn't realize when I shared my iPad that you could write on that too. That's cool. I love it. Let's see. So you said that's weird because I can see it on the screen, but I can't see it on my iPad. So anyway, so then the u, you don't multiply it, right?
Mhm.
And then Julie, so what's the derivative of square root of x? Remembering that x is really square root of x is really x to the 1/2.
Oh, would it be negative 1/2?
What else?
Oh, 1/2 x to the negative 1/2.
There you go. Yep. Now what?
Check if I did that. I don't think I did. Okay. And then it's all over v squared. And so, oh, I think this is where I might have messed up, because my thought was it would just be x, right?
That's correct, because it's the
Okay.
square root of x, but then you square it, and that's really nice because it made the square root go away.
Yeah.
Well, that's correct. In one sense, you're done. That's the answer. Now it's kind of ugly. It'd be easy to screw up the algebra and not know what to do here, but you're done with calculus right now.
Oh, was that the answer?
Well, yes and no. I mean, I don't know if my open math would take that as an answer or not. It might say simplify, or it might say good job. But I just want you to understand, calculus is now over. That's the
Mhm.
derivative.
No, it's
But if I was about to use it and plug in like x is 7, that's a horrifying thing to plug it into. And so if there was a way to clean it up, I wouldn't blame my open math for expecting you to do that. And it would certainly be to your advantage to do it.
Mhm.
So, you know,
So, okay.
can you
So then
clean
it would
that mess
just-
up is I think that's harder than the calculus, cleaning that mess up.
Yeah.
What would you do?
Well, I think my first move would probably be to change that square root x to the half.
Mm-hmm.
And then I just start distributing everything.
Mm-hmm. I'm gonna show you something later, so I'm making a copy of it. So yeah, since this is x to the 1/2, so you tell me what happens when I multiply it by 14x.
And this is where I mess up most because that half exponent like trips me up really bad.
Yep.
So would it be 7?
No, because the half is not in front of the x. It's not a number, it's an exponent.
Okay, so
Let me ask you a simpler question. What if it was like 4 times x to the second times x to the third?
oh, you would just add the exponents.
Yeah.
It'd be 4x to the 5th.
Notice I didn't tell you what to do. You actually already know. You just gotta think about what you know.
Yeah. Oh, so it'd be just 14x to the 3/2.
Mm-hmm.
Okay.
So you need to be more confident in that, so practice that. But yeah, it's
I've
1
never-
plus the half, which is 1/2. Which is,
Yeah. Okay.
that's right.
Plus 5x to the 3/2.
Not 3/2. The 5 doesn't have an x.
Oh. So it'd just be to the 1/2.
Yep. Cody's on it. So that takes care of that. And now you got even worse. You got minus everything.
Mm-hmm. Would you just switch the signs on that?
Yeah, you could just switch them all and say, you could just say right now in your mind, oh yeah, they're all going to be minus. Okay, fine. And then proceed.
So that'd be, and then this would be 7/2, right?
Yep, because now the half is actually a number, so that's exactly right.
And 2 minus 5/2. Right?
No, because it's negative a half. You're adding 2 and negative a half, not 2 plus a half.
Oh. 3/2.
Per half. And then minus again.
And is that to the negative half? Because, or no, what am I doing? Sorry.
Take your time.
That'd be to the half, right?
Good job.
Okay.
You have x to the 1 and x to the negative 1/2, and 1 plus negative a half is positive a half.
5/2 again.
It took me a little while to figure out half powers, so don't
I'm just-
feel bad. It's really tough.
Yeah.
I see a fraction and my body just reacts so adversely.
Yeah, I was the same way. Like after you get used to them, you're like, okay, this isn't so bad.
I hope to get there one day. And then, okay, negative 1/2. Okay. And that's to the negative 1/2 because there's no x.
Good job.
It looks terrible, if I'm honest.
They're fine. Now, what do you notice? Do you notice that there's, because of these plus and minus signs that I'm highlighting, there's actually 5 terms there. Can you add any of them together?
Yeah.
Yeah. Notice this is an x to the 3/2 and this is an x to the 3/2. And so I could add those together, right? And again, it just sucks that there's fractions, because now I got to go, instead of 14 minus 7 or something, it's like 14 minus 7/2. And so,
Oh, you have to. Yeah.
yeah, should be thinking it was 28/2 minus 7/2, which is 21/2. And so,
Okay.
21 halves, and then the description doesn't change. It's still x to the 3 halves.
Then the 5 halves cancel out because there's a plus and a minus. Right?
No, because these aren't the same. In other words, let's see.
Oh, they're not to the same power, or not power, but
Well, these two are, but their coefficient isn't the same. So
yeah,
still subtracting, like it's 5 minus 5 halves. So that'd be 10 halves minus 5 halves.
could be.
Just 5 halves again. And then the x to the negative 1 half doesn't have any other like terms, and so you're just going to stick with that. So that's better, but it's still a horrifying answer. Would you agree with that?
Yeah, it still looks pretty bad.
Let me show you something really cool that you could do with this, though, that's going to suddenly just make the whole thing come out into the sunshine. Let me show you a couple cool things. One of them would be, see how all the top, all the fractions are over 2?
Yeah,
I don't like fractions over fractions, so you tell me, how could I get rid of that?
you can multiply out the denominator.
Yeah, so if I multiplied top and bottom by 2, what would I have?
It would all be over 2x.
Yeah. And all of those 2's would be gone. So now I just have 21, no 2 anymore. 21x to the 3 halves plus 5x to the 1 half minus 5x to the negative 1 half over 2x. That's better, right?
Oh yeah.
Now here's something I doubt you would notice, but notice the same thing is true with the x's. Like, what would happen if you multiplied the top and the bottom by x to the 1 half? Why did I pick that?
They all have that in common, so that would.
Yeah, like what happens to this term when you distribute that? Because you got to multiply that by everything. What's 21x to the 3 halves times x to the 1 half?
Oh, it's 21 to the second power.
Yeah, that's exactly right. 21x to the second. That's really nice. What happens to this one?
That's just 5x.
It's just 5x. What happens to the last one? Something really awesome happens to the last one.
That just becomes -5.
Yeah, because it's x to the 0, which is 1. So it's just minus 5. Now on the bottom, what do you have? 2x to the what?
To the 1 half.
1.5. Yeah, Adam. So 1.5 or 3
Yep.
times.
3 halves.
So it's like it's still there, but that looks nicer. Like it's at a place now where if I have to actually plug in x's 2, like I'd far rather plug it into that last one.
Yeah.
But again, my point is, we were done with calculus way back here for that red one. It's just that, if I can clean the algebra up to make the thing look a little nicer. I don't know what my open math does. It could say you're wrong until you give that last answer, or maybe it just tells you you're right every time and calls you lazy for not simplifying it. I don't know what it does, but
I was liked having it like everything multiplied together, but like it didn't like when you simplified it.
Well, there's obviously, you got to be awesome at algebra to survive that simplification we just did.
Yeah.
And it's been my experience that people aren't that good. Like, that's really ugly. So I mean, you have to be good at algebra to not screw up that.
Yeah, that.
Like you said, even if you understand the rules of exponents, you probably aren't that good at it with
For
fractions.
some reason I just threw that all out the window when I started doing homework. So thank you.
Yeah, good questions. All right. See you tomorrow.
Yep. See ya.